One of the three wise phenomena, magnetism. Another one, electric charge. And finally, force and motion. And so for tonight's quick session, I thought I would play around with the three wise phenomena in some different demonstrations and kind of see what kind of a reaction I can get from you. Let's go and have a look at the bench. One of the little demonstrations I wanted to share with you is this. You've probably seen something like it. Just a series of coils of copper wire, and one end connected here to the positive, the other end connected to the negative of a power supply. So I can apply a voltage to the coil. Because this is copper, it's a conductor, and conductors have lots of free electrons. They've got electric charges that can be moved if you apply a voltage. The other part of the activity uses a small magnet with a couple of nails stuck onto it. So just a very small magnet, some nails stuck onto there. They're made of iron, so they will stick on quite well. And when we put the little magnet with the nails in the middle, you can see it's quite free to spin. Let's just see what happens when I put a voltage on to this little device. We can see there immediately our compass, our magnet in the middle, jumped. It moved around. I just turned it off and it relaxed. We'll try it again, and it moved. As I mentioned, the copper coil is full of electrons. They have electric charge. When we apply the voltage from the power supply, that actually puts those electrons into motion. They start flowing. We create an electric current. As soon as we have the electric current flowing in the coil, we generate a magnetic field. And that magnetic field in the coil then creates a force back on our little compass in the middle, making it move. So that's just one example of how these three principles interact. Here's another simple demonstration of those principles. We have a toy motor, a gearbox connected to a wheel. When I put some voltage across the motor, not surprising, we get it to work. So again, we have the electric charge of the electrons in the coils, in the copper in the motor. We put those in motion by applying a voltage. That generates a magnetic field that in fact reacts against the magnets that are already in the motor, leading to more force, movement coming out. And so it's the same principles turning up again. But we can see this actually now working in reverse. We have two motors, the same, hooked up. We've seen how one works as a motor, but if I hold on to this and I put the motion in, what was a motor is now a generator. So here I'm putting in the force, my energy, rotating it, moving that in a magnetic field, and that's then generating the electric current, which goes to the other motor, where the process is reversed. So a generator and a motor, it's the same three principles. So let's take a step towards chemistry. Here, in a tank of salty water, I've got two carbon electrodes. They're actually the leads out of a couple of pencils, and I've got them connected to a power supply. And at the moment, I'm just slowly increasing the voltage between the two electrodes. And here we see the start of hydrogen coming off one of the electrodes, and the voltage as it goes up in a moment, we'll see oxygen coming off the other electrode. We understand this is the electrolysis of water. But what we often don't think about are those charged particles moving between one and the other. We can't see them. And we also don't really focus on the chemistry, not the real chemistry of what's happening. So here we are tearing water apart. We've got hydrogen leaving. We've got oxygen evolving at the other electrode. But in our classes, we tend to just talk about the electrochemistry of what's going on. There's a lot else happening. And one of those other things which is going on is to do with acids and bases. We're taught a lot about acids and bases in high school chemistry. We're introduced to the concept of pH. One of the things we often don't focus on is pH is really a concentration of hydrogen ions. That means it's a charge. And so all the other things we've been talking about today are to do with charges, motion, and magnets. So I've loaded vinegar into the top channel, labelled acid, and I've put ammonia into the lower channel, which will now be caustic or basic. I'll add some blue pH indicator, which I've made from boiling up red cabbages. And we can see that in the acidic liquid, the indicator goes bright red. In the base, the indicator will turn green. But remember now, we're actually looking at ions, charged particles. That's giving us the colours. And that's important in our next activity. So we've looked at acids and bases and electrolysis and charge and magnets and current. Here's a tank with 2 electrodes filled with salty water and a pH indicator. Here is a small strong magnet that I'm going to put under the tank between the 2 electrodes. So it's not in the water, it's not touching the electrodes, but we have a magnetic field now coming up through the water. I've also got a little stand to hold a couple of other magnets, which I'll place. There's a gap under the bottom, which allows the fluid in the tank to flow and pass between the 2 electrodes. So now we have a very strong magnetic field that's going top down, and we're able to pass a current, that current that we saw electrolyzing the water. Now when we apply the voltage, we see a number of things happening. We can see bubbles. We can see the color changing. And we can see very rapid movement. That's movement across the tank. So all of this is happening even when we don't see it. So as we electrolyze the water, we're making charged ions. And those ions are moving, but they're moving with a magnetic field on top of them. And so that results in another force, which is pushing that flow across the tank to the right-hand side. We can see the color is changing, and that's telling us the pH is changing. And we know that because the hydrogen is bubbling off. We're losing hydrogen ions, so the pH has to change. This process is called magnetohydrodynamics, and it's actually used to pump coolant through nuclear reactors. But for me, I think it's just beautiful.